Hi, and welcome to Statistics 1, Lab 10. The goal of this week's lab is to conduct a binary logistic regression. And we covered this in lecture this week, and you'll see that doing a binary logistic regression in R is very similar to doing just a regular multiple regression in R. There's a slightly different function, and as you saw in the lectures, there's some sort of different statistics that we need to look at. There's odds ratios, the Wald tests, classification success, and so on. So I'll show you how to get those statistics here in R. So the example we're going to deal with is based on some real research done by a former colleague of mine, Sherry Diamond, who is in Chicago. And she does work at the intersection of psychology and law. And so with this experiment or this study, what they did is they had participants, and there were 100 of them, watch a videotaped sentencing phase trial in which the defendant had already been found guilty. So they watched this trial. There's a defendant, and the defendant has been found guilty. Now the jurors, and these participants are made to think that they're the jurors in this trial, they have to decide whether the defendant deserves the death penalty. This may seem odd for some of you not in the United States, but in some states here we still have the death penalty. And often is the case that jurors have to decide whether a guilty defendant, whether they should get the death penalty or just a life sentence in prison. So they have to make that decision. So this is a good example where the dependent variable has to be just binary. They have to vote for the death penalty or life sentence. There's no in between. We can't make this continuous. So just 0 or 1. Do you want the death penalty or do you want a life sentence in prison? And the initial verdicts are what's given in the data set. I again commented this out. Make sure you've got your right working directory. I've commented out the install packages, but you'll probably need to install these two new ones. We haven't used these before. So AOD and QuantPsych. So you may need to install those. I've already done that just to save time. So let me get started here by loading the packages and reading in the data. And I'll read them into a data frame called BL for binary logistic. And that looks good. No problems. If we want to look at the data, let me give you a glimpse. I'll use the edit function. Here's what the data look like. So we're trying to predict whether jurors will vote for the death penalty or not. This is actually a hot topic of research in psychology and law, in the United States at least, is what makes people think that this person deserves the death penalty? Well, there are a number of variables that people use to try and predict that. So how dangerous do they think that this person is or could be? How much do they believe in the process of rehabilitation in the prison system? How much do they believe in punishment just as a form of retribution or justice or learning? Then there's just will it promote general deterrence? Will it deter other people in the society from committing such crimes? Will it promote specific deterrence? Will it promote this person to be a better citizen, even in prison? And do they believe in incapacitation? And all of those things are rated on a 1 to 10 scale. So just like, how dangerous do you think this person is? How much do you believe in the rehabilitation programs in prison on a 1 to 10 scale? And do those predict who will vote for the death penalty and who will vote for a life sentence? And we also have just subject ID. So that's the data set. We could look at some summary statistics just to get a feel for what's going on in the data. most importantly, we could look at verdict and see that the mean is 0.48. That means it's about a 50-50 split, which is good for binary logistic regression. If you have an overwhelming majority that say voted for the death penalty, then none of this would work, right? There wouldn't be variance in the dependent variable to predict. So this is great. We're right at about 50%. And notice that it's binary. The minimum is 0, maximum is 1. The others, danger, rehab, punish, these are going to be all our predictors in the regression. Notice they're all on a scale of 0 to 10, as I mentioned. And there's nice variability in these as well. So the means are around 4 or 5 with standard deviations around 2 to 3. So these are really nice data. These aren't exactly the data from Diamond and Casper, but they're very close and based on that study, which was a pretty neat study. Okay, so let's go back to the script. Now we can run a binary logistic regression, and it's actually really easy in R since you've done so many regressions. The only trick is we're going to use this slightly different function called GLM, and that stands for Generalized Linear Model. And that's one of the topics in the last week of the course because it sort of prepares you for more advanced courses in statistics. Almost everything we've done in this course makes this assumption of linear relationships between the independent variables and the dependent variables, or the predictors and the outcomes, right? But you could have any type of function relating x to y, right? So the way to test that, or the way to test different types of relationships other than linear ones, is instead of using just LM for linear model, use GLM for generalized linear model. And then after you put in your regression equation, you'll see there's a comma here. You use the argument family, and then designate which kind of function you want to test. So we want to do a binomial regression. You could put in family equals Poisson, for example. There are several you could put in there, and that's how you do nonlinear regressions. So it's actually really easy to write the code. The trick is understanding the output, as you've seen in the lectures. You don't get simple, regression coefficients where, the slope is for a 1 unit increase in x, it's the predicted change in y, because, we're not testing linear functions anymore. So this is pretty simple. There it is. I'm going to call it LR fit for linear, not linear regression. I should have changed that. But let's call it LR fit. It's logistic, logistic regression fit. That's what it was. And I'm just going to put in verdict as my outcome variable, tilde, and then all of the predictors that we think might predict whether someone votes for the death penalty or for a life sentence. Then we'll use the summary function to get as much information out of that as we can. Let's run it. And here are the results. Now remember, this looks a lot like the output from a multiple regression. We have an intercept, and then we have lots of predictors. We have the estimate, standard error, a z-value, and a p-value. And the only trick is this estimate, remember, is the logit, which is not really that intuitive of a statistic. So we'll go ahead and we'll convert those logits into odds ratios, and we'll conduct Wald's tests. But you can see that some of them are significant and some of them are not. So how dangerous you think this criminal is a predictor of whether you vote for the death penalty. So it's positive, so death penalty was 1. So if you think of this person as being extremely dangerous, then you're more likely to vote for the death penalty. In contrast, if you really believe in the efficacy of the rehabilitation programs in the prison system, then you are less likely to vote for the death penalty. You're more likely to vote for life sentencing because you think this person might be able to live, a fulfilling life in prison and be rehabilitated. So that one is also significant, but in the opposite direction. Turns out punishment is not significant. General deterrence is. So if you believe that if by sentencing this criminal to death, you will generally deter these types of crimes in society, then you're more likely to vote for the death penalty. And turns out the more specific deterrence is not significant, nor is incapacitation. So we have looks like just 3 predictors that are significant and 3 that are not. Okay, so if we go back to the script, we can get confidence intervals around those estimates, and there's 2 ways to do it. The first way is the confidence intervals using profiled log likelihoods. That's typical for logistic models. And then the second way is just using standard errors. And they're not that different is the point. So you see 0.11 to 0.48, 0.11 to 0.475, so almost the same. So either way is acceptable. It's just the first way is typically is more common. But again, it's nice to see 95% confidence intervals. You could report these along with the original estimates. So back to the script. One thing that we talked about in lecture and how do you evaluate the overall model is you look at the model chi-square, and the way we do that is we can compare the chi-square for our model versus what's called a null model. A null model is one that has no predictors in the model. So we can get the chi-square for that model, get the chi-square for our model, and then get the degrees of freedom for the null model and the degrees of freedom for our model, and then do a chi-square test to get a p-value to see if there's a significant difference. Now, since we have 3 significant predictors in the model, we know that this is going to come out to be significant, but this is just how you do it. So we have a chi-square of 24 and then degrees of freedom of 6, and you see there's a very large p-value. And if you go way back up here, you can see the chi-square for the null model was 138, and the chi-square for our model 114. So the difference here, sorry, this is the difference. I think I just said it was for the model. Is 24. Is that difference significant with 6 degrees of freedom? Yes, it is, because it's a very low p-value. That's what we're testing there. Okay, so we have a model that's significantly better than the null model. We could get walled tests for each of the coefficients, and that's why we need this library AOD. So let me just run them all together and start at the top. So first, the walled test for danger. It gives me a chi-square of 10 with 1 degree of freedom, because remember what the walled test does is it says how much would your chi-square change if you dropped this one predictor. And we know that this should be significant because danger is a significant predictor in the model, and in fact we would have a change in chi-square if we drop danger. And so that's a significant wall test. These should correspond to the significance values or p-values that we got in the regression analysis. So again, punishment, that looks like it's significant, whereas general deterrence, not significant. Here, this one's a little different. Now it's significant, but the other 2 are not. Again, we could also get odds ratios. To me, these are a little more intuitive than the logits. So like if I were to write up a binary logistic regression or present it at a meeting, I would probably just present these. So here are the odds ratios for each of the coefficients, and the way to do that is just to take the LR fit, which is where we saved the model, get coefficients, and take exponents, the exponentiated coefficients. And what you see is, remember, a logit of 0 corresponds to an odds ratio of 1. That is, like, we have no basis for prediction. So these last two, if you remember back at the top, the logits were about 0, and here the odds ratios are about 1. As it's a 1-to-1 chance that they're going to go death penalty or life sentence. You just don't know. Whereas here, we have the odds are 1.3. There's a slightly greater chance that they're going to go with the death penalty than with a life sentence. And then, again, rehab goes the opposite way. We can also look at our classification results, and there's a function called class log. And again, we just take our LR fit, and we want to look at verdict. That is, how well did we predict the actual verdicts. And what it gives you are these sort of contingency tables or class tabs. And here are the raw numbers, here are the percentages, and here is the overall percentage. So we're classifying 71% of the cases correctly. Again, that's better than chance. Chance would be 50%. So 71% is not great, but we're doing all right. So it's a significant model. We have 3 predictors that are significant, and we're classifying 71% of the cases correctly. So we're getting some insight into why some people would vote for the death penalty and some people wouldn't. And finally, the last thing I'm going to do is just show these in graphically. And what I'm doing here is putting them all together. So, well, putting the significant predictors together, and then we'll look at the non-significant predictors. So we can demonstrate the result graphically. Here are the significant predictors, and what I've done is basically put on the y-axis the predicted LR fit, not in terms of 0, 1, but in terms of the logit. So you can see that the more dangerous you think the criminal is, then the more likely you are to vote for the death penalty, where death penalty was scored as 1. And again, rehabilitation goes the opposite way. General deterrence goes the same way as dangerous. Then if we wanted to do the same thing for the non-significant predictors, here's what those look like. Of course, those are going to approach a flat line, right? They should be near horizontal because we just don't have any basis for prediction. So if I know like what your attitudes is about punishment in general, that's not going to help me in predicting whether you're going to go for the death penalty or a life sentence. It's right about around 0. And same thing for the others. So that's what the non-significant predictors look like. Okay, and that's the end of this script. That's the end of this lab. That's all you'll need to do the next assignment, which is going to ask you to do something very similar. We'll ask you to do a binary logistic regression analysis and then answer questions based on things like odds ratios, walled tests, classifications, tables, and so on. So good luck with the assignment, and I'll talk to you next week in Lab 11.